All right. Good news, bad news. 12.4, day number 1. Good news. We're almost done. 12.4, that's the last section we are doing this year. We have 3 days, day 1, day 2, day 3. The other good news is way easier than section 12.3. Bad news. You know how there are those times when you learn how to do things the long way and then somebody shows you a shortcut? Well, that's what 12.4 is. 12.4 is a shortcut for section 12.3. In section 12.3, we were going through and finding the slope of the tangent line using a formula, and that formula was big and long. We had to work it all out. Section 12.4 is how to use something called the derivative to do the exact same thing. So 12.4 is going to give us all of the shortcuts. There are dozens and dozens of shortcuts for finding the derivative in calculus. We're going to cover the first 3, the 3 main ones. And then you'll see the other ones if you decide you're going to take a calculus class at some point. On the AP exam for calculus, they do use that definition of a derivative, which we would call the slope of the tangent line. That formula that we kept doing in section 12.3, that formula is on the AP exam, so it's important that we cover 12.3 and that we know how to do it the long way, finding the slope of the tangent line using that difference quotient. But 12.4, that's where we really want to be. This is where the calculations go really fast, so that's good. Not complicated at all. The derivative of f of x is, according to our book on page 766, it is this. First of all, instead of calling it the slope of the tangent line, they're going to call it the derivative, but it's really the same thing. And then this is the notation, or at least one of them, that books typically use. This is a pretty common notation. So your original function is f of x, and then when you go through and find the slope of the tangent line, we use this notation, which is also the same thing as the derivative. So in section 12.3, we called it finding the slope of the tangent line at any point. And in section 12.4, we're going to call it the derivative, but it really is the same thing, and then this is the symbol for a derivative. What our book says on page 766 is that the derivative can be defined this way for any function, f of x. It is equal to f, and then that apostrophe there, most math teachers, most math people, read that as prime. So for any function f of x, f prime of x, or the derivative of f of x, or the slope of the tangent line at any point for f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all of that over h. So again, if you were to take a look at what this is that formula that we were using for the slope of our tangent line in section 12.3. But here, instead of calling it the slope of the tangent line, we're going to call it the derivative, and it's equal to this. There are 3 main shortcuts that we're going to cover. We'll do one of them for 12.4 day 1, one of them for 12.4 day 2, one of them for 12.4 day 3. I'll show you those 3 shortcuts. Then we'll do a practice test, and then we'll do the test. So that's the direction we're headed. 12.4 day 1, the shortcut that we're going to be looking at looks like this. It is something called the power rule. What that means is if you have something with an exponent in it and you want to do the derivative, instead of doing this big long formula, you can do something else. The power rule for derivatives looks like this. If f of x is equal to, and what we just said is that the power rule here implies that there is an exponent. So let's say we have our function f of x, and let's say it's x to a power. In general, they're going to use a letter like n for the power. So this could be x squared or x cubed or x to the 10th power, something like that. If you have your original function and it looks like this, and n is a real number, then the derivative of this equation looks like this. It's n times x to the n minus 1 power. So instead of going through and doing this big, huge calculation, which takes about 5 or 6 lines of work to do, if you have something that looks like this, instead of using our slope of our tangent line and the limit with this difference quotient to figure out what the slope of the tangent line would be, the slope of the tangent line can just be found by using this. And if you look at what is happening in this process, in the original, we have x raised to the nth power. And in order for us to get the derivative, what happens is that we put an n in front. So what we're going to do is we're going to take whatever our exponent is, and that's going to come in front. And then we need to make the exponent smaller by 1. So when you look at that exponent up there, it's n here, and then we put the n in front, and then we reduce the exponent by 1. So that's what the rule says. Let me give you one quick example of what that might look like, and then we'll jump in and do some problems. Let's say that you had like f of x is equal to x to the 3rd power. What that means then is this. When you do the derivative, we want to take whatever was up in the exponent and we put that in front. Well, we had an exponent of 3 here, so that's going to be 3. And then we multiply that by x raised to the exponent, but the exponent was n, and here it's n minus 1, so it needs to get smaller by 1. So it was x to the 3rd power here, so it's going to be an x squared here. So you take the exponent and you put it in front, and then you make our exponent smaller by 1. This replaces this. This takes about 5 seconds. This takes a couple minutes at best. So it really is a huge shortcut. It really does help us out. All right, so I'm going to run through and do some problems using that idea. Our directions for example 1 are going to be to find the derivative. We're just going to rattle off a whole bunch of these. These go pretty fast, especially compared to section 12.3. Find the derivative. All right, so when you go through and you find the derivative, you're going to be calculating f prime of x. And again, if you have a variable raised to a real number power, you simply take your real number and you put that in front. So that's going to be a 7. And then we still have x as the base of our exponent, but we need to reduce the exponent by 1. So that's going to be to the 6th power. And that's our answer. That's it. Letter B. F of x is equal to 5x to the 3rd. Okay, so this looks a little bit different. We have a number here in front. We have the number 5, so we need to know how to handle that. But it is easy, and it's exactly what you would think it would be. We had a 5 here, so I can just copy that down. And then we do the derivative of our base and our exponent. So the derivative of x to the 3rd power, we take the 3 and we write it in front. And then we reduce the exponent by 1. So the derivative of x to the 3rd is 3x squared, and then we have that 5 in front. And we can just multiply those together. So our final answer would be a 15x squared. I'm continuing to use f of x here in front, but this could be f of x or g of x or h of x, could be anything. We said that you should be able to go through and calculate the derivative if you have a real number for the exponent. I've done integer values so far, so it's been pretty easy. This is still just about as easy, and you can use your calculator to help yourself out a little bit. But if you don't have a nice integer here for your exponent, it would look like this. Well, I'm going to be doing the derivative. I have a number in front, so I can just copy that down. So that's just going to be 3 times. And then the derivative of x raised to a real number, in this case x raised to the 7/3, we take the exponent and we write that in front. And then we have x to the, and we need to reduce the exponent by 1. So we're going to be doing this. It was 7/3. We need to subtract 1 off of that. So you end up with this for your answer. You'd want to go through and multiply 3 and the 7/3 together. So if you multiply these two together here, 3 times 7/3, well, you can throw that into your calculator if you want. Otherwise, the 3 here would cancel with the 3 in the bottom, and we would just get the number 7. So when you multiply those together, you just get the number 7 in front. That was a little bit harder than what we, or a little easier. Nope, sorry. This is a little bit harder than what we did in letter B. Letter B, we just had 5 times 3 in front, so it was a nice 15. Here we have 3 times 7/3. So again, if you want, you can use your calculator for that. I'm not going to have you do anything without the use of a calculator, so that would be fine. And then from there, we do need to reduce our exponent by 1. So we have 7/3, that's what it was originally, and we want to subtract 1 from that. So again, you can grab your calculator, or you could find a common denominator and do this by hand. That's not very hard either. We're doing 7/3 minus 1, but if you find a common denominator, we would want to think of that 1 like 3/3, and 7/3 minus 3/3, that is 4/3. So when you go through and you do your calculation, if you're going to do it by hand, you should get 4/3 just by finding a common denominator. Otherwise, you can definitely use your calculator for that too. So your final answer is 7x to the 4/3 power. Again, that process is a lot faster than going through and doing that slope of the tangent line that we were doing in section 12.3. I'm going to do a couple more of those. I have a letter D, E, and F, and then we'll do an example 2. And that'll be it for today's notes.